In this video, we're going to talk about approximating the definite integral value, our left sums and our right sums, using the areas of rectangles. We're going to do this time with the help of Excel to help do the calculations for us. So let's do example 7 all over again, but instead of doing it by hand, we're going to just jump right into Excel. I have taken our rate function. So notice here our rate function f prime of x is this third degree polynomial. I've come on over to Excel and I've put an input value starting at x equals 0, and here I've put the f prime function. So in the calculation we were doing previously in example 7, we were trying to approximate the definite integral from 0 to 8. So remember, that's the interval from x equals 0 to x equals 8. We did it with 4 subdivisions. So we created 4 rectangles. We evaluated the function at x equals 0, 2, 4, 6, and 8, and we used those heights when we were doing our calculations. We needed those heights because they were the heights of the rectangles used in our left sum calculations and our right sum calculations. So the first thing I'm going to do in Excel is I'm going to evaluate the function at x is 0, 2, 4, 6, and 8. So I come on over here to Excel. I first started it at 0, and I'll put in 2, 4, 6, and 8. Drag my formula down. All right, there's the heights of the function. The next thing we did when we performed our rectangle calculations back here is we found the areas of these 4 rectangles. So for example, in our left sum, our first rectangle spanned from x equals 0 to x equals 2. And since it was a left sum, this rectangle's height came from the left side of the interval. It came from the height of the function at x equals 0. So you plug x equals 0 into the function, we got the value 240. And if we come on over to Excel, you see that that height would be here in our first row of values. And we wanted to find the area of that rectangle. Well, let me just create a new column here that's going to be the areas of rectangles, I'll label it. The first rectangle had a base length 2, and its height came from this cell here, cell B2. So the formula would be equals base 2 times height, cell B2. The next rectangle spanned from x equals 2 to x equals 4, so it also has a base length 2. Its height came from the height of the function at x equals 2. So in Excel, notice that's right here, cell B3. So the next cell's area is 2 times the function height at x equals 2. And it continues. It's always the base 2 times the height of the function. So we'll just drag this down, and we have all those areas of the rectangles. I'm just going to go off to the side now, and I'm just going to make a little label for myself. I'm going to need to calculate a left sum, a right sum, and I'll also find an average of the two, because that's a nice estimate of the definite integral in the end. There's a feature in Excel called sum. Sum will add up a series of cells that you highlight. So I am interested in finding a left sum first. Remember, the left sum will add up these 4 rectangles that used the heights at x equals 0, x equals 2, x equals 4, and x equals 6. We do not use the height at x equals 8 when doing a left sum. So I'm going to tell Excel I want the left sum to equal the sum of the areas of the rectangles starting at x equals 0 and including x equals 2, x equals 4, and x equals 6. Notice what I have here, x equals sum parentheses, and I highlighted the cells starting at the area cell corresponding to x equals 0, but not including the very last cell, because we don't have a rectangle with a height corresponding to x equals 8. and it gives us 1640. And remember, that's what we got before when we did it in the previous video by hand. All right, we're going to do a right sum next. We should get a value of 1320 like we did when we did it by hand, but let's examine that again. When we do a right sum, the very first rectangle in a right sum, its height is the height of the function at x equals 2, because that first rectangle's height comes from the right side of the interval. There is no rectangle that corresponds to the height at x equals 0. We skip the height at x equals 0. So we have a rectangle with height at x equals 2, one at x equals 4, one at x equals 6, and we have one at x equals 8, but we don't include one at x equals 0. So when I do this right sum in Excel, it will equal the sum, parenthesis. I highlight all the cells starting at x equals 2, extending up to x equals 8, but I do not include the rectangle that has a height at x equals 0. And yep, we got 1320. Lastly, we like to average those two out to get a nice estimate of that definite integral. And there is a feature in Excel called average that gives you the arithmetic mean. It just adds up all the values and divides by the number of values. So you just set it equal to average, parenthesis, and then highlight the cells you want it to average out. And if you get 1480, which is the same thing. So my estimate of the definite integral from x equals 0 to x equals 8 is 1480. All right, let's do it again. We're going to move on to the next page in the packet, and it's the same function, you see. We're still trying to estimate the definite integral, but instead of using 4 rectangles this time, we're going to use 8 rectangles. We're going to fill it in with smaller, thinner rectangles. Hopefully that will give us a better estimate. So first, let's kind of think about what this would look like, and then we can use Excel to help us with the calculations this time. Our first step when we're about to do our Riemann sum, our left sums and our right sums to make these rectangles, is to identify the length of each of base of the rectangles. So to do that, we're going to take the length of our interval and we're going to divide that up into 8 subdivisions this time. So we always divide by the number of subdivisions to see how long each subdivision interval will be. All right, so this time the length of our interval is 8. It extends from x equals 0 to x equals 8, and it said divided up into 8 subdivisions, 8 rectangles. So obviously the base of each rectangle will be 1. Our first rectangle spans from x equals 0 to x equals 1. We're doing a left sum, so I extend the height up on the left side. The first rectangle would look like so. The next rectangle goes from 1 to 2, then 2 to 3, and so forth. Remember, each of these left sum rectangles, the height of your rectangle has to come from the height of the function on the left side. The very first rectangle has height f prime of 0, and the last rectangle has height at x equals 7, f prime of 7. There is no rectangle for our left sums using the height at x equals 8. All right, that's pretty good. We see that these rectangles extend beyond the function a little bit, so it's overestimating a bit, but not as bad as when we had 4 rectangles. We're going to use Excel to actually find all these heights and find these areas and add them all up, but that's what it's going to be calculating, is that area there. The right rectangles, the first rectangle spans from x equals 0 to x equals 1. The height of that rectangle is the height of the function at x equals 1. There is no rectangle corresponding to the height when x is 0. So this first one is the height when x is 1. All right, the next one is the height when x is 2, and then x is 3, and so forth. These are our right rectangles, the height of the function on the right side of each rectangle. And this one ends at the height of the function when x is 8. Remember, your left sum rectangles did not use x equals 8. All right, and this one again looks like it's a little bit of an underestimate. It's not quite filling in the area between the rate function and the x-axis. The other one looked like it was overdoing it. When we average them out, we might get a good estimate. All right, let's come on over here to Excel. I'm just going to erase out what we did before. I'm going to erase everything except this starting point. So we're still starting at x is 0. We still need the rate function in there, calculating the function value when x is 0. This time, though, we want our x's to span from x equals 0 up to x equals 8 with increments of 1. There we go. And I'll drag my function down. Again, the areas of our rectangles are just base times height. This time, though, the base of our rectangle is always 1. So the area of each rectangle is 1 times the function height. And drag it down. We're going to do a left sum, a right sum, and an average. And remember, left sum will equal sum of all the areas of the rectangles starting at the x equals 0 height and extending all the way up, but not including the function value at x equals 8. Left rectangles, you're skipping the very last one. Right sum, same idea. It's the sum of all these areas, all these rectangle areas, except we don't use that very first one because there was no rectangle that had a height corresponding to x equals 0. All right, we average it out to get a nice estimate. The left sum was going over, the right sum was going under, and we get an average of 1490. That's a good estimate. All right. You'll see on the next page it says, well, can you do it for 50 rectangles? Can you do it for 100 rectangles? How about 500 rectangles? I'm going to go ahead and just jump up here to 500, and the posting of the full solutions will include the values for 50 and 100. Clearly, I'm not going to be drawing that, but we could use Excel to help us calculate the value of this estimate if we had 500 rectangles. We come back here and do a little tiny bit of side work before we calculate it on Excel. If we were doing 500 rectangles, we are going to have to think about still the same ideas. We still have to find the base length of each one of those little teeny tiny rectangles we would have. And it's always the length of the interval divided by the number of subdivisions, the number of rectangles. So in this case, we're still spanning from x equals 0 to x equals 8, so the length of the interval is 8, but we're dividing it up into 500 pieces, and we're going to get 0.016. So that is the base length of each rectangle. Little teeny tiny rectangles. Now you could create a little formula in here that for your x values, it equals the cell above plus 0.016 and drag it down. But alternatively, I just wanted to show you there is a fill feature that does this automatically for you. To use the fill feature, put your cursor in the cell with the starting value in it. So you have 0, which is the starting value. You put your cursor in that cell. It feeds it a seed value, a starting value. On your Home tab, you see over here, there's a button that says Fill. It's got this arrow on it. Click the Fill button. Select Series. So Fill Series. I want to have my x values go down a column, not a row. So select Column. I want linear growth. I want it to add 0.016 over and over. I want it to go 0, 0.016, and then add another 0.016, and add another 0.016. That's linear, with a step value of 0.016. And I want it to stop at 8. Remember, it's spanning from x equals 0 to x equals 8. This will automatically just fill in the x's for you. There you go. Then I have my function value. I just drag that down with a double click. The areas of my rectangles. Area will be base times height. Each of these little teeny tiny rectangles has a base of 0.016. So the base 0.016 times the height of the function. Drag it down. And then I do my left sum, right sum, average. Remember, always, 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 a left sum will use the very first function value at x equals 0, which is our starting left side, but it will not use the very last height. So I'm going to extend this all the way up, but then I do not use the height when x is 8 because it's a left sum. There's no rectangle using x equals 8. But the right sum, we use all the rectangles except the very first. So my sum skips the one including x equals 0, goes all the way up and does include x equals 8. And then I average them out. Look how close together now the left sum and the right sum are. The left sum's 1494, the right sum's 1492. So our average is around 1493. Those left sums and right sums are getting closer and closer together the more and more rectangles we're doing. So I think hopefully you're getting the idea of this now. As we use more and more and more rectangles, we're filling in that area between the rate function and the x-axis in a more accurate manner.